From last time, what we did was we defined the probabilistic definition of entropy, and we also talked about how to do energy distribution calculations. Okay, so the probabilistic definition of entropy, it is a description of entropy written in terms of probabilities of the different outcomes for a system. Okay, for some system that has T possible different outcomes, and so the examples that we care about are T number of different energy levels, and an example we did last time was a T-sided die, right? We said a regular 6-sided die of equal probability of each side coming up. We did an easy entropy calc for that example. We also looked at this system here. Okay. So how many energy levels are there here? 11, technically. Ground state or zero energy will always be the bottom, will always be the first energy level you will consider in any example problem, okay? U sub I is our notation to give us our energy level. So zero energy is U sub 0. Energy level 1, U sub I has energy 1. Okay, we said it might be arbitrary units. Maybe I'll give you joules, could be kilojoules, could be whatever. Okay. The number of molecules that we have in the 0th level, n sub 0, is equal to 10. We can count them in a system this small. Okay. The number of molecules in level 1, or n sub 1, is 9. Okay. So n total is the sum of all of these 55. Okay. And if we want to calculate the total energy of this system, what do? Energy of the level times the number of molecules in the level, and sum it across all the levels you have. Okay. So the total energy for this system, U total, is the sum of n sub 0 times 0 plus n sub 1 is equal to 9 times energy level of 1, up to 165 energy units. How do I get the probability that any one of these 55 molecules is in the 3rd level? What is the probability of the 3rd level? So it is n sub 3, number in the 3rd level, over the total number, 7 over 55, which I don't know, is 0.127, right? So the probability of any given level is given by this equation here, just our general probability equation. Number in that energy level, total number of molecules we have. And if we want to just do a check for ourselves, make sure everything sums to 1. Okay? So once we have all these probabilities, we can now calculate entropy for this system using the probabilistic definition, which looks like this. Okay? And is somewhere on your equation chain. All right, so S is equal to negative N, the number of total molecules, times Boltzmann's constant, times the sum over the T is the total number of energy levels I have going from ground state or 0 up to, in this case, 10. I really wouldn't have to include 10. I see that there's nothing there and probability of 0. Okay, I'll take the probability times the natural log of the probability of that level and sum over all of my levels, something like this. Okay. Negative 55 kb, 10 over 55 times the natural log of 10 over 55, plus 9 over 55, and on up across all the levels. The probabilistic definition is an approximation of the statistical definition, okay? It's suitable for very large values of n. So how come I don't need probabilistic definition for small values of n? Do I even need it for the system that's on the board right now? Not really, okay? Because I can do multiplicity of this system, all right? M factorial is 55 total things. The categories on the bottom, I have 10 factorial, 9 factorial, 8 factorial. So I can do this. None of these numbers require it, all right? So my expectation of you on the homework and on the midterm is that either the word probabilistic definition will be expressly stated so you know to use it, or you won't have a choice. The numbers will be so big, or an n won't be given. You'll just be given probabilities of levels, and then you'll be asked to give a relative measure of entropy. Leave it in terms of n, but you'll have to use the probabilities. It would be your only choice, right?